Hi everyone, today I'm going to be talking about capacitors and the specific things that you will need to know for OCR, A-level physics. But firstly, before I start with the learning outcomes, I would like us to look at what actually a capacitor is. So a capacitor is simply an electrical component that stores energy by separating charges. This is very powerful. This is actually used in a lot of touch screens, depending on what type of phone you have or tablet. And that's what basically controls what you're doing. It momentarily stores energy, and that's how the screen works. I can give you more information on that when we go back to class. So what is its structure? It simply consists of two metallic plates that are separated by from each other by an insulator, a dielectric material, and I'll go back to that word later on as well. So it is two plates, metallic. We usually draw it like this. So these are the metallic plates, and in between them is the dielectric material. It could be air, or anything else. It's an insulator, that's the important bit. So this is a better symbol here of a capacitor. That's how we draw it as an electric symbol. But capacitors tend to come in different shapes and sizes. But for when we draw them in a circuit, an electrical circuit, we draw them looking like two lines are equal in size. So that's our metallic plates. And the gap between them is the insulator. So what's the important part of metallic and components and insulators is that metallic parts, so conductors, these plates allow electrons to flow through them. However, an insulator does not allow electrons to flow through it. So this is going to be a bit different to what we're used to with other components, and that's why it has its own chapter on its own. Now I'm going to go on to explain how capacitors kind of charge and discharge, so part B of the learning outcomes. And I will go back to what capacitance is in a second. So now if we consider a normal circuit, for example, here. Now this is just a cell connected. So remember, the long line is the positive side of the cell, the short line is the negative side of the cell. I have a switch here that is open, so now I have already an even distribution of my electrons that are already free in the wire to move, but they're not moving yet because they don't have any energy or any electric field across the 2 points. And then I have my capacitor connected here. I'm going to see step by step what happens when I close that switch. This is a good point to mention that conventional current is not very helpful to think about in this case. This is the only case where we're going to see how electrons are actually flowing. So let's have a look. So what I have a second circuit now showing that I have closed the switch here. So the switch is closed. But in this case, once the switch is closed, I know that the electrons will start flowing. We already said that this is the negative terminal, this is the positive terminal. In terms of electron flow, I know that once I have a complete circuit, electrons will be repelled from this end, so from the negative end, because negative charges repel negative charges. And you'll see the electrons instead start building up about this plate right here. So you have electrons moving to this end. Now the problem is that since the middle of the actual the center of the capacitor is made of a dielectric material, like a specific insulator, even air is an insulator, the electrons cannot flow through it. So all these electrons are piled up on this plate here, and they cannot go through it. So you have an overall charge of minus Q once it starts building up. Now, in the meantime, at the same time actually, the same thing is happening to the other side, but in a different way, because all the electrons are negatively charged. On this side of the wire here is actually attracted, all the electrons are attracted to the positive charge of the battery or cell, and hence they will start moving to the positive terminal of the cell. So it will look something like this. So a total of negative electrons moving around to this side. Now that means that this plate, that means that this plate right here is actually left with a deficiency of electrons, which means that it will acquire an overall positive Q charge. So just so we double check, in a circuit, electrons flow when they're connected to a cell or battery, and they can travel between since they can't travel between the plates of a capacitor, since it's an insulator, then what you have is the electrons are removed from the plate connected to the positive terminal. So this one, they're removed, which leaves you with a plate with a positive charge Q, so plus capital Q, and then you have electrons are gained on the plate on the opposite side, which leaves it with an overall charge of minus Q. And in general, the biggest point here as well to make sure that we remember is that when the capacitor is fully charged, the net charge, so this is it being fully charged, all the electrons have accumulated on the capacitor plate and electrons have been removed from the other plate. So the net charge here is 0. Because what we mean by net, we mean total charge. So if I do plus Q plus minus Q, is the same thing as plus Q minus Q, which gives me the total charge of 0. Now this separation of charges leads to energy being stored, and we'll have a look through it in 1 second. So another few points. We know that when electrons flow, you have current in a circuit. So immediately at time 0, when we close the switch and the current is the highest, but after a bit, when the capacitor is fully charged, the current is 0. The other point I wanted to mention, for example, if the EMF of the cell was, let's say, 6 volts, then after the capacitor's charge, the capacitor will also have a voltage of 6 volts across it. So it has stored 6 joules per coulomb. So just to summarize again, while the capacitor is charging, the current decreases through it, because obviously you have less and less electrons flowing since they're accumulating at different ends. And at the same time, the potential difference across the capacitor is increasing to the maximum EMF by the time it becomes fully charged. We will look at how time affects this well later on in the second part of the video I will make. The second video that I will make on capacitors. But for now, it's just making sure that you understand that charges moving is what creates current. And the less the charges are moving, obviously the current decreases until there's no more motion of electrons, which means no more current once it's fully charged. But at the same time, the potential difference is increasing across the capacitors too. Also, a great point to mention here is that the conservation of charge. So the plates have an equal but opposite charge. You can't have more charge on one plate than the other, and that is again an effect of conservation of charge. So we're going to continue with what is capacitance and how to calculate it, and its units as well, which are quite new things. Okay, so what is, how can we calculate capacitance? So you need to be able to define it, and through the definition it's very easy to see the actual equation. You're given the equation, but just make sure when I mention certain symbols, you don't mix them up. So what is capacitance? It is defined as the charge stored per unit potential difference across it. So basically how much charge is stored per unit, per PD. So we look at the definition, is the charge stored. So capacitance is a capital C, the symbol for it is a capital C, which is equal to the charge stored, so Q. So the unit, the symbol for charge is Q, divided by the PD across it, so by V. Once again, C stands for capacitance, is a capital C. But the unit is something that you haven't seen before. The unit is farad, capital F. Then we have charge, which unit has a unit of coulombs, capital C. So please make sure you don't confuse C for capacitance with C for coulombs. It's very, very important to not mix those two up. And then you have a potential difference, which is measured in volts. So this is a nice equation because it shows you that capacitance actually is a fixed quantity for each capacitor. So if we have a capacitor that has a capacitance of 500 microfarads, then that's a fixed quantity. And if we rearrange it, we can see that Q is equal to CV. Now, C being a constant for a specific capacitor, that means that the charge is directly proportional to the potential difference across the capacitor. So the bigger the charge stored, the bigger the voltage across it. And last part of this introduction to capacitors is how to define the unit farad. You don't need much, you just need to see the equation and see what the units are. So 1 farad, which is this, 1 farad, is simply 1 coulomb per 1 volt. That's the, or per volt. This is what you definitely need to be able to use, to remember as well. So defining a quantity, when we define a quantity, we have to use other quantities. So we're defining capacitance as the charge per unit potential difference. But when we're defining units, we're defining units with other units. So 1 farad is 1 coulomb per volt. So define quantities with quantities and units with units. You can still use the equations, it makes it simple and easy to follow. And this is a really nice question. It says capacitor with capacitance 200 microfarads is connected to a 10 volt supply. So already as I'm reading through it, I can underline and know my capacitance is this much. I know my voltage, my potential difference is this much. I also know that I have a unit prefix which I need to convert. That's 10 to the minus 6. That's a micro, Greek letter mu, lowercase. And remember that stands for 10 to the minus 6. And then I need to calculate the number of electrons. Now that seems a bit familiar because I know that charge is equal to the number of electrons times the charge of an electron. So the total charge of something is the number of electrons times the electric charge of one electron. So I need to calculate basically the number of electrons in this case. I am given C and V. I know that Q is equal to CV. So I'm just going to multiply to calculate the charge stored on the positive or negative plate, because remember, positive and negative plate of a capacitor have equal and opposite charges, minus Q and plus Q. So however many electrons are stored here, they are removed from this side. So whatever is stored on this plate, it is the same amount of electrons removed from this plate, because that's what gives charge to the plates, is the electrons and how many of them. So let's continue. So we have 200 times 10 to the minus 6 times 10, which will be 200 times 10 to the minus 5. We will be working a lot with very small capacitances. So it's very, very important to remember the units prefixes. So you'll see micro, nano, maybe milli sometimes as well. But we will come across it more and more often. I can simplify this into 2 times 10 to the minus 3 coulombs. And now I know, since Q is equal to NE, I have the total charge on the positive plate. So then I simply rearrange, N is equal to Q over E, and I can calculate how many electrons make a charge of 2 times 10 to the minus 3 coulombs. So that's 2 times 10 to the minus 3 divided by 1.6 times 10 to the minus 19. Remember the elementary charge, and you should get about 1.25 times 10 to the power of 16. That's a lot of electrons, but it's expected, right? Which is roughly about 1.3 times 10 to the 16 electrons. So going back to the learning outcomes, we talked about capacitance and how to calculate it, and about the unit. We talked about charging and discharging a capacitor. Now we're going to start looking at how to calculate total capacitance in a series, total capacitance in parallel. You also need to be able to prove these expressions, and then we're going to look at how to analyze circuits that contain capacitors. There's also a practical activity, which obviously will be hard to go through now, but I will add a link in the description so that you can have a look at people who have done the videos with equipment as well. The idea of why we do need to connect capacitors in series or parallel is because capacitors come with their own values. So for example, one could be 200 microfarads, another one could be 500 microfarads, and so on. They have fixed numbers, but you might not be able to find one that is designed to have 233 microfarads, for example. So in order to get the specific capacitance that you require for a specific use, so we use them in every way, and to get that specific amount, you need to either combine them in series, in parallel, or a combination of series and parallel together. And we need to have a look at how we are able to combine them and calculate total capacitance, and how to prove that. Now we're going to start first with the parallel combination. We have done something similar like this with resistors, where we looked at how current, voltage, potential difference and resistance are linked together. But in this case, so we basically worked on R is equal to V over I. So this is the equation that we use to analyze how resistors work when they're combined together in parallel or in series. Now in this case, since we are working with capacitors, our main equation and focus is this equation. So we will be working mostly with what happens to potential difference and what happens to the charge across each capacitor. Now, first things first, we know that in a parallel circuit, the EMF of the cell will be the same as the potential difference of capacitor 1 and the potential difference across capacitor 2. So the EMF is equal to V1, which is equal to V2. We also know that, and this is Kirchhoff's second law, And we also know that charge is always conserved in a circuit. So the total charge Q that enters the circuit, for example, it will be equal to the charge that is stored across capacitor C1 and the charge stored across capacitor C2. So Q is equal to Q1 plus Q2. Now, obviously, this could involve more than two capacitors in parallel. It could be 3, 4, 5. Depending on what the question gives, you should be able to show the addition of that or the expression of that. And since we know that this equation is what combines QC and V together, now we have an equation and we have an expression that shows equality. I will substitute in this expression, in this equation, what Q stands for. So it stands for C times V, capacitance times potential difference, which is equal to the capacitance 1 times the potential difference times the potential difference across capacitor 1 plus the capacitance of capacitor 2 times the potential difference across capacitor 2. But we already know that the EMF is equal to V1, which is equal to V2. So all the V's here are equal. So we can leave them as 1. So V is equal to V1, which is equal to V2. So I'll leave them all as a V. CV is equal to C1 V plus C2 V. If I divide both sides by V, so I have V is a common factor, so C1 plus C2. Divide both sides by V, and I end up with an expression that the total capacitance is equal to the capacitance of capacitor 1 and capacitance of capacitor 2. So when I connect capacitors in parallel, the total capacitance is more than the individual capacitance of each capacitor because they add up. In resistance, with resistors, we saw this was the opposite case. So the total resistance was less than the smallest resistance of one individual resistor. So this is the opposite what happens with capacitance. Now, if I wanted to increase the amount of energy stored by my combination of capacitors, it would be best to combine them in a parallel combination, since Q is equal to CV, and if we have higher capacitance for a specific voltage, then we also have a higher amount of charge stored. So once again, we're only interested in what happens with capacitance. So we will use the equation for capacitance. And we will also use Kirchhoff's laws. So Kirchhoff's second law says that the EMF is shared between the components. So the potential difference across C1 and C2 is combined together is equal to the potential difference or the EMF of the cell. So here we have already an equation. So the V total is V1 plus V2. And also the charge stored by each capacitor is the same. So Q1, Q2 are both equal to each other. So we'll name it just Q. Now what happens is that you have electrons building up on this plate. There is no transfer of electrons between the plates. So there is no transfer between the plates because there's dielectric material, so an insulator that stops electrons flowing. So what happens is that the electrons that build up here push the electrons on this side, so they repel them, and there will be a minus Q charge here, a plus Q charge here. So overall, the charge across the capacitors is a total of 0. But then since obviously you have a plus Q charge here, then you have a buildup of electrons on this side, which is minus Q, plus Q, and so on. So both plates store the same amount of charge, regardless, if they're in series, regardless of whether they have different capacitance. So that's one very important bit. It's quite similar to what we say about how current in a series circuit is the same along each point, but in this time we're looking at charge. So once again, I have this equation here, I have the equality of the charges here, and I will be using this equation to substitute values in there. So I will rearrange to make V the subject of the formula for this equation. So we have V is Q over C, and then I will substitute for each expression here. So I have Q total over C total is equal to Q1 over V1 plus, so I'm just simply substituting, remember, plus Q, oh sorry, C1, keep making these mistakes. So Q2 over C2. So this is my expression. I already said that they're all equal. So we have all of this Q's, let's name them all Q total, because they're all the same either way. And I will just take this opportunity to make a common factor, take a common factor out. I will divide both sides by QT, so that means they're gone. And I'm left with the expression of 1 over total capacitance is equal to 1 over C1 plus 1 over C2. So this is what we saw for parallel circuits in terms of resistance. But in a series circuit, the total resistance of resistors, don't confuse resistors with capacitors. This is something to remind you of what we done and what we proved last time when it came to resistors. So this is it. If you remember how to prove the resistors, this will be easy as well to implement. So this is a question that we can use to just practice a bit. It says to calculate the total capacitance in the circuit. So what we have is we have a capacitor that is in series with a parallel combination of capacitors and a battery. Then we have a voltmeter for part 2 to calculate the reading on the voltmeter. The first thing we do in circuits that involve series and parallel combinations is that we deal with the parallel combinations first to see how much this combination of capacitance this combination gives you, and then if you were to replace it with a single one, and then you deal with it as a series capacitor. So we start off firstly with these two parallel ones. We know that the total capacitance, we proved it, of capacitors in parallel is just simply adding them together. So we have 500 microfarads plus 200 microfarads, which gives me 700 microfarads. You can see here I didn't need to convert these units yet, because it simply leaves it nicer and neater, and I'm just adding them, and we're adding the same units. Obviously, if one of them was nano and the other one was a micro, you'll have to do some changes to your calculations. So if I were to replace this combination, I will get 700 microfarads. So I can redraw this to make it simpler. Now I'm working with 100 microfarads and 700 microfarads connected in series. And I need to be able to calculate the total capacitance of the two. Since I know that in series, then I have to use 1 over C total is equal to 1 over C1 plus 1 over C2. And that is 1 over CT is 1 over 100 plus 1 over 700. Also, when you do place this in the calculator, remember you are getting an answer 1 over capacitance total, so you'll need to invert it. So whatever answer you get, you do 1 over the answer. Or alternatively, you can put it in the calculator looking like this. You will get an answer of 87.5 microfarads. So this is my total capacitance of the whole circuit. So I broke down the parallel, joined it into the series, and I found the total capacitance. The next thing that we need to calculate is the reading on the voltmeter. This point requires us to use another equation. Q is equal to CV. In this case, I know that my total capacitance of my circuit is this much. And I also know that my total voltage of my circuit is 3 volts. So I have capacitance and I do have voltage. That will actually give me the total charge stored by the whole circuit. So Q is equal to 87.5 times 10 to the minus 6. This is the point where I do need to include what the unit is, because I'm using it in an actual equation that requires me to have coulombs as a unit, times 3 volts. So you have about 2.63 times 10 to the minus 4 coulombs stored by the whole combination of capacitors. The reason I bothered finding the total charge in this circuit is because I know that this capacitor, since it's in series combination, so the charge stored by each plate is exactly the same as the total charge, as well as between these 2 points. So the total charge in a series circuit is a charge stored by individual capacitor as well. So I know my charge now, and remember I want to find the voltage across this capacitor. So I will use again the same equation. Q is equal to CV. I will actually rearrange because I need to find the voltage. So it's going to be Q over C. I will use the total charge because it's the same charge stored by the 100 microfarad capacitor and the charge that's stored between the combination, the parallel combination. So that will be 2.63 times 10 to the minus 4 divided by the capacitance of the capacitor I'm trying to work with. So that's 100, well, the one I'm trying to calculate the voltage across. So that's 100 microfarads. And that will give me 2.6 volts. So we have discussed so far how to prove the capacitance, done a bit of calculation as well. So capacitors in series, capacitors in parallel proved. And we have done an analysis of circuits containing capacitors. We will see more about resistors later. So usually we do combine resistors with capacitors to simply protect them from burning or from too high current. But we will see the analysis of those type of calculations later on when we see logarithmic expressions and exponential expressions.